Good evening friends. Today we are going to discuss about semiconductor and carrier concentration in intrinsic semiconductor. Before we are going to discuss about this topic, we need to know what is semiconductor and also the types of semiconductor. Then we are going to calculate the density of electrons in the conduction band value and the density of holes in the valence band value. Right, Ne and Mh. Right. Generally, low resistive materials are called semiconductors. Here, the electrical conductivity and the resistivity values which lies in between those of conductors and insulators are called as semiconductor. Right. According to band theory, the band gap value for a semiconductor which starts from 0.5 electron volt to 1.5 electron volt. And also the another important characteristics, at the temperature 0 Kelvin, semiconductors act as insulators. When temperature is applied to a semiconductor, then it will act as a conductor. So semiconducting devices are a very good phenomena. In recent days, it is used in various fields of science and technology. Right. But what is my topic today is, today we are going to discuss about the carrier concentration in intrinsic semiconductors. Right. First we should know the types of semiconductor, then we will discuss about this carrier concentration in intrinsic semiconductor. The types of semiconductor: based on composition, semiconductors are classified into elemental semiconductor and compound semiconductor. Based on purity or concentration, the semiconductor is divided into two types, that is intrinsic semiconductor and extrinsic semiconductor. So intrinsic semiconductors are 100% pure form semiconductors and extrinsic semiconductors are again divided into two types, that is N-type semiconductor and P-type semiconductor. Alright. So today we are going to calculate the intrinsic carrier concentration value for a pure semiconductor. Right? This is 100% pure semiconductor. The best example for intrinsic semiconductors are germanium and silicon. Alright. Now, what I am going to do is, I am going to draw the intrinsic semiconductor band diagram over there. You can look at it. Alright. So, at temperature 0 Kelvin, so in the case of semiconductor we have conduction band and valence band. So this will be represented as valence band and this area will be conduction band, and you know this is your Fermi energy level and this is your conduction band energy level and this is your valence band energy level. Alright. And the distance between the conduction band and the valence band energy level represents and the valence band is 100% filled. Valence band when at temperature T equal to 0. Right. Suppose when thermal field is applied at temperature is greater than 0 Kelvin, which means in the presence of thermal field, what will happen? So in the semiconductor, valence band, conduction band, valence band, and this is Fermi energy level, conduction band minimum energy level, and the valence band maximum energy level. Right? For conduction band, maximum energy level is infinity, and the valence band minimum energy level is minus infinity. Right? So initially, when temperature equal to 0 Kelvin, conduction band is 100% empty and the valence band is completely filled. When thermal field is applied to a semiconductor, right? So already we knew that all the valence electrons are completely occupied in the valence band, in the absence of thermal field. Now when field is applied, what happens? An electron in the valence band which moves from valence band to conduction band. Electrons from valence band move to conduction band. When the thermal field is applied. Further stronger field is applied, almost all the free electrons which moves from valence band to conduction. Right? So, at temperature is greater than 0 Kelvin, a few electrons from valence band which is transferred from here to there. Right? At here, under equilibrium condition, number of electrons in the conduction band which is equal to number of holes in the valence band. At equilibrium conditions, number of electrons in the conduction band equal to the number of holes in the valence band. This is the most important concept in the case of intrinsic semiconductor, or for calculating the carrier concentration value for an intrinsic semiconductor. Alright. By using this concept, we are going to calculate the carrier concentration value for an intrinsic semiconductor. Right. The symbol of carrier concentration value is Ni, and we know that under thermal equilibrium conditions, number of electrons which is equal to number of holes in the valence band, right? And carrier concentration Ni squared equal to Ne dot Ns, right? This is what we need to calculate today, right? Ne represents density of electrons in the conduction band, Nh represents density of holes in the valence band. First we need to calculate density of electrons in the conduction band. Afterwards we need to calculate density of holes in the valence band. Okay, so once again, under thermal equilibrium conditions, number of electrons in the conduction band which is always equal to the number of holes in the valence band. Don't ever forget, right? Now I am going to calculate Ne, right? So here density of electrons in the conduction band which is equal to integral E conduction band, the energy level value or which starts from EC to ends from infinity, which means EC is minimum energy level and the maximum energy level is up to infinity. That is why we are putting here EC to infinity. And we need to know what is Z of E dE. Z of E dE, which represents density of energy states. We also need to know how much or how many number of energy states are available in the conduction band energy level. We should know that is called density of energy states. That value already we know that pi by 2 into 8 mv star by h square whole power 3 by 2 into e power of dE. So this is density of energy state value. This is already calculated, right? Here mv star, which is nothing but effective mass of an electron, right? And another term f of E. So here f of E represents Fermi-Dirac distribution function. The Fermi-Dirac distribution function, that is 1 by 1 plus exponential of E minus EF by kBt. Right? Fermi distribution function, which is nothing but is the probability of an electron given by the given energy state. Right? If f of E is 1 means the electron is occupied in the energy state. If f of E is 0 means there is no electron is available in the energy state. So these two terms are most important for calculating the density of electrons in the conduction band value. That is N. Alright. So here look at the term e power of. So this is the energy level term. So here instead of e power of, we need to write E minus EC whole power of. So that is instead of E dE equal to pi by 2 8 m E star by h squared whole power 3 by 2 into E minus EC whole power of into dE. Right? Why I am writing now? The total energy level minus minimum energy level. Total energy level minus minimum energy level. So this one, equation number 2, and no, this one you can take equation number 2. This one is 3 and this one is 4. Right. Now we need to substitute these two values. That is substitute equation 3 and 4 in equation number 1. Now we need to substitute the equation Z of E dE values and f of E values from 3 and 4 to equation number 1. Right. So the density of electrons in the conduction band is given by, that is ND, is given by integral EC to infinity Z of E dE. Already we know that 5 by 2 8 m E star by h squared whole power 3 by 2 into E minus EC power of into dE into f of E value 1 by 1 plus exponential of E minus EF by kBt. So now we have substituted the value Z of E dE and f of E from equation 3 and 4, and we substituted in equation number 1. Alright, from this, when electron which moves from conduction band to valence band energy level, we requires more energy than kBt. We require more energy than kBt. So we can write energy distribution E minus EF is very much greater than kBt. So which means we need more energy for transferring the electron from conduction band to valence band to conduction band. So from this we can write E minus EF divided by kBt is very much greater than 1, or exponential of E minus EF divided by kBt is very much greater than 1. So from this equation number 5, instead of writing 1 plus exponential of E minus EF by kBt, we can write simply exponential of E minus EF by kBt. Alright? So compared to 1, this value will be more, so we can neglect 1 from here. Alright? Now we need to substitute this value in the equation number 5. Right? So number of electrons in the conduction band Ne equal to integral Ec to infinity pi by 2 into 8 Me star by h square whole power 3 by 2 into E minus Ec whole power of divided by, instead of 1 plus exponential of E minus Ef by kBt, now we simply neglect 1, so we can write exponential of E minus Ef by kBt. I think one more term is there, that is d. Right. So now we have substituted. Right. Our next step will be Ne equal to integral Ec to infinity pi by 2 into 8 E star by h square whole power 3 by 2. The denominator term exponential of E minus Ef by kBt should go to numerator. So E minus Ec whole power of into exponential of, is very simple, when denominator term goes to the numerator, you simply interchange the term. Inner term Ef minus Ef by kBt is very easy. Alright. Now we need to solve this integral, right? Or we can write Ne equal to, take this term is a constant term, so take it outside. Pi by 2 into 8 E star by h squared whole power 3 by 2 integral Ec to infinity. So E minus Ec whole power of into exponential of Ef minus Ec by kBt. Right. So now we need to solve this integral. For that, I am going to assume E minus Ec as x kBt. From this, you can write E equal to Ec plus x kBt. Differentiating this with respect to x. So d equal to kBt. So this will be 0. So kBt dot dx. Right? And the limits are when E equal to Ec, if E equal to Ec, put x equal to 0. When E equal to another level is infinity, put x equal to infinity. So the limits are 0 to infinity. So instead of E minus Ec, put x kBt. When E is here, instead of E, right? Where it is? Yeah. Instead of E of minus, sorry. Instead of E, put Ec plus x kBt. Instead of dE, I forgot to write dE here again. Yes, dE, right? Okay. Instead of dE, you have to write kBt dot dx. Instead of E, you have to substitute EC plus x kBt. Instead of B minus EC, substitute x kBt. And the limits are 0 to 1. E equal to EC, put 0. And E equal to infinity, put x equal to infinity. Right. Right. I'm going to substitute all these values in the above equation. So, number of electrons in the conduction band Me equal to 5 by 2 into 8m E star by h squared whole power 3 by 2. Integral. So, instead of EC you have to substitute 0. Instead of infinity you have to substitute infinity. 0 to infinity. So instead of B minus EC, you have to substitute x kBt whole power of. Right. Next, exponential of EF minus, right? What is our EC plus x kBt? So minus of EC minus into plus minus x kBt divided by kBt, and we have one more term, that is dE. What is dE? kBt dot dx. So I think we have substituted in a right manner. So instead of EC to infinity, we need to substitute 0 to infinity. E minus EC you have to put x kBt, and instead of EC minus x kBt and kBt dot dx. Okay, everything is substituted. So don't ever forget what is our ultimate aim is. We are going to calculate the density of electrons in the conduction band. We are calculating Ne, right? So Ne equal to 5 by 2 into 8m E star by h squared whole power 3 by 2 integral 0 to infinity, right? Here x power of into kBt power of, right? Yes. Now we need to separate these two. I am going to separate the exponential term into two. That is exponential of EF minus EC by kBt is one term. Another term, the exponential of minus x kBt divided by kBt is another term, and we have kBt dx. Right, here kBt power 1, here kBt power of, so we can write kBt power 3 by 2. So we can get it in here. Right, and here kBt will cancel. Right, so remaining we can write Ne, number of electrons in the conduction band equal to 5 by 2 into 8m E star. kBt power of kBt power 1, so you can put it here kBt divided by h squared whole power 3 by 2 into integral 0 to infinity. So remaining only x power of is there, and here exponential of EF minus EC divided by kBt is remaining, and here exponential of minus x is remaining, and dx is remaining. Okay, so take this term out of the integral, right? Number of electrons in the conduction band Ne equal to 5 by 2 into 8m E star kBt by h squared whole power 3 by 2 into exponential of EF minus EC by kBt into integral 0 to infinity. So x power of is here, e power minus x is here, and dx. And we need the integral value for this. Integral value will be root 5 by 2 or 5 power of by 2. Substitute the value here. Right. So number of electrons in the conduction band N equal to pi by 2 8 m e star kBT by h squared 4 power 3 by 2 into exponential of EF minus EC by kBT into root pi by 2. The value for integral of 0 to infinity x power of e power minus dx is the final solution is root pi by 2. So that is why I am putting it. Right, very good. This was the here. This is pi power 1 and this is pi power of. So pi power 1 and pi power of, and you know that pi power 3 by 2 you can put here. So n equal to 1 by 2. So already 1 by 2 is here, 1 by 2 is here. So you can write 1 by 4. So 8 pi power 3 by 2. So 8 by m e star kBT by h squared whole power 2 by 2 into exponential of EF minus EC by kBT. Right. So this is our final equation for the number of electrons in the conduction band for an intrinsic semiconductor. Alright. Again, we can further simplify it. We can write n equal to 2 into 2 pi m star kBT by h square 4 power 3 by 2 into exponential of EF minus EC by kBT. So this will be your final answer for number of electrons in the conduction band for an intrinsic semiconductor. So we know that if you want to know this, no, I will write it here. You can check it here, right? So here, what is that? 8. So 8 power 3 by 2. You can write 2 power 3 by 2 into 2 power 3 by 2 into 2 power 3 by 2. Right? 2 power 3 by 2 into 2 power 3 by 2. You can write 2 cube into 2 power 3 by 2. Right? So take it outside. You will get 2 into 2 power 2 cube, which is nothing but 8. So 3 by 2 or 3 by 2 is 2 cube. So you can write 2 into 2 power 3 by 2. So when you take it outside, take it to the part. Right. So this is the way we need to calculate the number of electrons in the conduction band. If you want to calculate number of holes in the valence band, if you need to calculate the number of holes in the valence band, come here, right? So we have calculated and here we have calculated. If you want to calculate NH, we need to consider the minimum energy level is minus infinity and the maximum energy level is EV. And here the hole is created, which means that there is no electron is available. There is no electron is available, so that the Fermi energy value will be 1 minus f of it, which means that it is not occupying the given energy state. So don't ever forget. Thank you very much. In the next class, we are going to discuss about number of holes in the valence band. After calculating NH, we need to multiply with NE, then only we will be able to get the value of Ni, which is nothing but carrier concentration for an intrinsic semiconductor. Thank you.